The goals of a distillation system are to maintain an optimum production rate and to meet specifications that are set for its products. In this unit, we'll examine various factors that must be controlled if a distillation system is to meet its goals, and we'll see how control systems provide the control that's needed. For a distillation system, the term material balance means that the sum of the materials that leave the distillation column or tower must be equal to the feed that enters the tower. If the flows of materials are not balanced, problems could develop in the process. A distillation system's material balance can be controlled by controlling the flows of materials. This is a simplified illustration of a distillation system. The flows that make up the tower's material balance are the feed flow into the tower, the overhead product flow from the overhead system, the bottoms product flow from the tower, and the off-gas stream. The off-gas stream is the flow of gases drawn out of the receiver through this line. The flows of materials are controlled by control loops. Control loops consist of instruments and devices that work together to monitor and control the values of process variables, such as pressure, level, and flow. Control loops are part of the distillation system's control system. In our example, the flows of materials are controlled by a feed flow control loop, a bottom level control loop, an overhead product level control loop, and an off-gas stream pressure control loop. The feed flow control loop provides a means to control the rate at which feed flows into the tower. The bottom level control loop controls the level in the bottom of the tower by controlling the bottom's product flow. The overhead product level control loop regulates the level in the overhead receiver by controlling the overhead product flow. The off-gas stream pressure control loop controls the release of gas from the overhead receiver, which controls the pressure in the distillation tower. For a distillation system, the term energy balance means that the heat that goes into a distillation tower must be equal to the heat that goes out of the tower. The energy flows for a distillation tower can be divided into primary energy flows and secondary energy flows. Primary energy flows are associated with heat transfer into or out of the system. The primary energy flows for the system illustrated here are the heat input to the reboiler and the feed preheater, and the heat that is transferred out of the overhead vapor in the condenser. Most of the heat input to the tower from the reboiler and the feed preheater is removed by the condenser. Heat also leaves the tower in the products, in the gases that are vented from the system, and by heat transfer through equipment casings and piping. Secondary energy flows are associated with heat transfer in which the heat remains within the distillation system. For example, reflux transfers heat out of some of the vapors in the column and condenses the heavier components. However, that heat transfer is between two fluids within the distillation tower. It doesn't involve an external medium, such as air or cooling water. The amount of secondary energy flow is determined by the external reflux flow rate. Two major factors in achieving an energy balance are the rate at which the reboiler vaporizes liquid and the rate of vapor condensation in the condenser. If the system has a feed preheater, the heat that the preheater supplies must also be removed to achieve an energy balance. The energy flows are controlled by energy balance control loops. Each control loop consists of instruments and devices that work together to monitor and control the value of a process variable. In our example, the primary energy flows are controlled by a reboiler temperature control loop, a feed preheater temperature control loop, and a condenser temperature control loop. The reboiler temperature control loop controls the amount of heat that is sent to the tower. This temperature control is accomplished by regulating the flow of steam through the reboiler. The feed preheater temperature control loop controls the temperature of the feed by regulating the flow of steam through the preheater. The condenser temperature control loop regulates the amount of cooling that takes place in the condenser. Major temperature changes in this control loop are accomplished by starting and stopping the fans in this fin-fan condenser. The control loop makes fine or trim temperature adjustments by adjusting louvers in the path of the forced air from the fans. This system has one secondary energy control loop. It regulates the amount of external reflux that is sent back to the tower to control condensation in the tower. The term steady-state operation describes conditions in a distillation system when the process variables are changing in small amounts within prescribed limits. During steady-state operation, changes in the flows of material and energy are minimal and are handled by the control system. However, major changes, called process disturbances, can affect the material balance and the energy balance. Many process disturbances result from changes in feed composition. For example, let's assume that there's an increase in the feed's lighter components. We'll also assume that the heat needed to vaporize the lighter components is added in the preheater. When there's an increase in lighter components, there's a decrease in the amount of heavier components in the feed that flows down the tower. The decrease in heavier components causes the tower's bottom temperature to initially increase. The bottom temperature sensor that is part of the reboiler temperature control loop senses the temperature increase, and the control loop automatically decreases the reboiler steam flow to adapt to the new condition. With less heat added by the reboiler, and since there are now more lighter, low-boiling vapors, the tower's top temperature decreases. In response to this decrease, the reflux control loop decreases the flow of external reflux. Since more vapors are being condensed, the level in the overhead receiver increases. The overhead product control loop senses the increase and increases the flow of the overhead product. The change in the feed composition also affects the level in the bottom of the tower. Since there are more lighter components in the feed, the bottom level decreases. The bottom level control loop senses the decrease and reduces the bottom's product flow. In this topic, we looked at material balance variables and energy balance variables, and we saw how they can be controlled by control loops. We also saw how a distillation control system can react to a process disturbance. Process control systems can consist of many different combinations of control loops. The control system for a particular process is designed to meet the requirements for that process. But regardless of the process, a change in a process variable can disrupt the system's material and energy balances. Control loops are designed to restore the balances, but operators need to be aware of changes in their systems so that they can help ensure that products meet specification. Changes in the external reflux that flows to a distillation tower can affect the composition of the tower's products. When external reflux enters the tower, its lightest portion vaporizes and flows out of the tower with the other overhead vapors. The rest of the external reflux flows down the tower. The reflux helps to condense the heavier components of the vapors in the tower. A decrease in the amount of reflux entering the tower means that more of the heavier components remain as vapors and reach the condenser, where they are condensed and sent to the overhead receiver. The increase in vapors in the tower also raises the temperature in the tower. Now, an increase in the amount of reflux entering the tower causes more condensation to take place in the tower. As a result, more of the feed's heavier components are condensed and will flow back down the tower. And since more vapor is condensed, the temperature in the tower decreases. The tower's control system will react to either an increase or decrease in the tower's temperature. When there's an increase in temperature, the external reflux control loop senses the change and then increases the flow of external reflux to the tower. The increased flow of reflux condenses more of the vapors in the tower, and the temperature in the tower decreases. When the external reflux control loop senses a decrease in the temperature, it decreases the flow of reflux to the tower. In some distillation systems, the external reflux flow is kept constant. The amount of condensation is varied by changing the temperature of the reflux. Introducing cooler reflux into the tower has the same effect on product composition as increasing the flow of reflux to the tower. In this topic, we looked at how a tower's control system responds to changes in bottom temperature. We also looked at how product composition can be affected by changes in external reflux. Requirements for a product are sometimes called product specifications or specs. A spec is a value or a range of values for a physical property that is required for a product. Products are routinely tested to ensure that the specs are met. Testing can be done by direct composition measurement or by indirect composition measurement. Direct composition measurements are analyses that allow personnel to directly observe the percentages of components contained in a product. One type of instrument that is commonly used to perform direct composition measurements is a process chromatograph. A process chromatograph analyzes a product and provides a readout of the component percentages. The measurements made by the chromatograph can be compared against specs to see if any adjustments are needed to ensure that the product meets specifications. Indirect composition measurements are analyses in which one measured property is used as an indicator of another property. In other words, the measurement of a property is used to determine product composition. One common indirect measurement is boiling temperature. For example, since the boiling points of the components in a feed mixture are known, the components in a product can be indirectly identified by their boiling points. When a product is tested, its composition can be indirectly measured by recording the temperatures at which the different components in the product boil. Product specs are set by the demands of downstream processes and by the marketplace. Products must meet certain quality standards. For example, a downstream process may require a feed of predetermined quality. Sales contracts and marketing practices also require distillation systems to produce products that meet certain quality standards. Exceeding product specs or producing better quality product than is required is known as product giveaway. When product giveaway occurs, both product and energy are wasted. For example, a facility uses more utilities, such as fuel, than necessary. And in many cases, customers may not be able to use the products. Doing this can reduce a facility's profit margin. Product composition measurements are made to make sure that the products of a distillation system are on spec. For example, the tower represented here separates a feed that contains methylcyclopentane, or MCP, and cyclohexane, or CYC6. The MCP is the lighter component of the feed, and it is removed as the overhead product. The heavier CYC6 is the bottoms product. In this example, the spec for the bottoms product is 0% MCP. In other words, all of the MCP should be removed as overhead product. The spec for the overhead product is less than 5% CYC6. To help maintain product specs, samples of the products are taken and sent to the lab on a regular basis. Indirect composition measurements are then performed to determine the percentages of MCP and CYC6 in the products. Distillation tests are run on the products to obtain their initial and final boiling points. If the initial boiling point of the bottoms product is lower than normal, it indicates that there is some MCP in the bottoms product, so the bottoms product is off-spec. If the final boiling point of the overhead product is higher than normal, it indicates that the tower is too hot. When the tower is too hot, an abnormal amount of CYC6 is sent overhead with the MCP. If there is more than 5% CYC6 in the overhead product, the product is off-spec. If the tower is too hot, the bottom temperature could be too high. If so, it should be decreased slightly. Decreasing the bottom temperature allows more of the heavier component, which is CYC6, to remain in the bottoms product. This action may decrease the amount of CYC6 passing overhead, and it should bring the products back to spec. If the percentage of CYC6 in the overhead product falls too far below 4%, there is a danger of some MCP remaining in the bottoms product. To bring the products back to spec, the bottom temperature should be increased slightly. This ensures that as much of the lighter component as possible is boiled out of the bottoms liquid. In general, changes in a tower's operation should be made in small increments. Gradual changes allow time for the process to react and minimize fluctuations that are caused by overshooting the set point. Now, product specs and the way they're controlled involve a variety of factors. One of these factors is process lag. Process lag is the time between making a change in tower operations and having the adjustment take full effect in the tower. In some larger towers, the process lag is long, and it may take up to several hours for results to develop. In smaller towers, the process lag may be shorter, and a result may be seen more quickly. Well, in this topic, we looked at product composition. Specifically, we looked at product specifications and how these specs